need to talk about friction. I'll remind you from our earlier lesson that what friction is. It's the component of the contact force between two objects, the component which is parallel to the surface of contact. For our purposes, there are two kinds of friction. There is kinetic friction, the frictional force on something which is actually sliding, and then there is static friction, which is the frictional force on something which is not sliding. You recall the earlier example of the tilted tabletop with a coffee cup sitting on it. That would be an example of static friction. We're going to talk about kinetic friction first. It's, although you might not suspect it, it's actually the easier one to talk about. So I'm going to ask you to imagine the following experiment. I've got a box sitting on a horizontal tabletop. The surfaces between the box and the tabletop are not frictionless, and so if I give this guy a shove, he'll slide for a little while and come to a stop because the force of friction will be an unbalanced force. But what I'm going to imagine is the following. I'm going to imagine tying a string to the box, and I'm going to pull on it with some force F, and I'm going to adjust F until the box moves with constant velocity. In that case, we have that this force F, which I could measure, must be equal to what the frictional force is for this situation. This situation, of course, is I have a single box, which has a weight, which I'll call W, and a normal force, N, which in this simple problem will be numerically equal to the weight, but that vector, of course, points in the opposite direction. Note that what N measures is the force which is pressing the box and the surface of the table together. Okay, so N is a measurement of how hard the surfaces are pressed together. And so if I do this experiment, I will measure F, therefore deduce the frictional force, and the normal force I know is numerically equal to the weight of this box. So I will get some data point. Maybe it'll be right there. So next what I want to do is I want to get myself another box, put it on top. Identical box, okay, but now the weight becomes twice as big. The normal force becomes twice as big. And now if I pull with the same force that I did in the first experiment, I will find that it does not move with a constant velocity. I have to pull harder. In other words, if the normal force gets bigger, the frictional force gets bigger. Okay, so when I do this, I'll get a new data point. Okay. Guess what I'm going to do now? I'm going to grab another box, stick it up here. Now I got 3 boxes, so now the weight is 3 times what it was at the beginning. So the normal force is 3 times what it was in the beginning. And what I'm going to find is that, once again, to keep this guy going with constant speed, I have to increase this force F. So I get yet another data point. Okay, so here's the next data point I get. And guess what? I'll play the game again. Now I got 4 boxes. You see how it's going. Now the weight is 4 times bigger, the normal force is 4 times bigger, and once again I have to increase F. So I do that, and I get another data point. Finally, got 1 more box left. Might as well finish this experiment off. Now I got 5 boxes. The weight is 5 times bigger than 1 box. The normal force is 5 times bigger. The frictional force now, again, gets bigger. In other words, what I'm finding is the harder I press these surfaces together, the bigger the kinetic friction force is. So I get another point. And now I'm going to say, well, it looks like I have enough data here to see what's going on. So I say, well, let's see here. If I take and draw a line through those points, look how nice they line up in a straight line. And if you did this experiment, this is approximately what you would find. Okay? And let's say, what is it that we found? If we find that the frictional force depends linearly on the normal force, then we could write that F, better get this be a pen, okay, we could get that F is proportional to N, okay. And now we can ask ourselves, what else does the frictional force depend on? And for normal circumstances where the forces are not too big, what we find is that there is essentially no other quantity that the frictional force depends on. It does not depend on the surface area. What it does depend on is what the two surfaces are. For example, if the frictional force, if this were a frictional force between two very sticky surfaces, say sliding rubber on concrete, then the frictional force would be very big, and what we would get that this this curve here was much more steeply inclined. If this were a box made out of Teflon sliding on a Teflon tabletop, then what we would find is that this slope is very much smaller than the experiment that I've done here. But for any particular thing, all we have to do is measure what the slope of this line is, and we find out what the proportionality constant is of this proportionality. Okay, so I'm going to write then this very important equation, which says that F is equal to some proportionality constant, which is standardly called mu, or in fact mu sub k. The k stands for kinetic times n. I'm going to draw a box around that because that's something you really are going to need to know. So the kinetic friction is equal to mu sub k times n. The thing that really matters is how hard you press the surfaces together. You can do a little experiment yourself. Take your hands and press them together as hard as you can, and then try to slide your hands over one another. You won't be able to do it. You're not strong enough to overcome that frictional force. So the frictional force depends on what the nature of the surfaces is, but it also depends on how hard you press them together. So that's kinetic friction. And as I say, kinetic friction is actually usually easier to deal with because kinetic friction is always the same. You can always use a formula. We always like to have an equation we can stuff things into, right? Well, this, as long as the thing is sliding, then we've got we can easily calculate what the frictional force is. If the thing is not sliding, we cannot necessarily easily calculate what it is. One thing I should point out before we go on is that this is not a law of physics like Newton's first law is a law of physics. This, in fact, is an approximate statement of the way surfaces approximately act. It's not exactly true. Also notice that it isn't at all a vector equation. It's a very empirical sort of equation. Okay, that's not a vector equation because although f and n are each vectors, they always are perpendicular to each other. So there's no way that the vector f could be equal to mu sub k times the vector n. This is an empirical equation, and it's one which is useful, but if you press them hard enough, they'll weld together. So there all sorts of, if you really press them harder and harder and harder together, this curve is eventually going to not look like such a nice straight line. Okay, so now let's go to static friction. Static friction there is when a situation is when the object is not sliding. Okay, so here we have a situation, and there is no motion. Okay, the weight of the box down, the normal force up, and again I'm pulling with a force F, but I'm not pulling with a force big enough to actually make this thing move across the table. So we can see now whatever F is right now is what the frictional force F has to be because it's in equilibrium. If I pull with a little less force than this, well, I will find that it still doesn't move, of course. So that means that the frictional force is even less. Okay, if I pull with even less force than that, okay, so in essence, the frictional force is whatever if it's not moving, the frictional force is whatever it has to be in order to satisfy Newton's first law. Now you all know what's going to happen. Eventually, you're going to reach a point where F gets so big that suddenly this thing is going to not be capable. The frictional force will not be capable of holding it there any longer. Okay, and so there's a certain maximum amount of friction that you can get on this surface. Okay, so really and truly, this frictional force up here, I guess I should have called F sub max, because that's what I want to look at. Okay, so let's call this F sub max. Okay, and so what I'm going to do is I'm going to take this one box and I'm going to pull and I'm going to gradually increase the force until this thing pops away, and that'll tell me what the biggest force was. So I'll get some number for the maximum force I could have. And now I'm going to take and play the same game I did for kinetic friction. I'm going to take this guy and put him up here. Okay, and now what I'm going to find is that if I press the two together harder, it will take more force to pop this guy away. So I'll get another data point here. And I think rather than go through stacking these all up again, you can see what I'm doing. I'm going to say that what I'm going to get is a bunch of data points like this. And when I'm finally satisfied that I've got enough data to see what's going on, then I'll go and I'll draw a straight line through them all. And I will say that now I sort of understand what's going on. It is F max, which is proportional to the normal force. Okay, the most friction I can get is proportional to the normal force, and so F max is equal to some constant mu sub s times n. Okay, and so that's mu sub s is called the coefficient of static friction. It's always a little bit bigger than the coefficient of kinetic friction. You know that because when this box breaks away, it suddenly starts to accelerate. It doesn't go very, very smoothly. So at any rate, so if you want to know what the frictional force is on something which isn't moving, the best you can do is write an inequality. F has to be less than or equal to mu sub s n. So there's your physics there. Okay, so we got the tools we need now to do, as I've sort of promised, some Newton's first law examples, a little more complicated than those we've been doing already. So all the prep work is out of the way, and the next video then, and probably the next couple of videos, will be some little bit more complicated problems.